this lab, what we are going to do is we'll understand the various features of Intel Quartus Prime Lite Edition version 18.0. Then we'll create a project. Then we'll learn how to create a project in Quartus Prime. And then we'll make a design using block diagram or schematic based design entry procedure. Okay, so that we'll do. Then we'll use Intel Quartus Prime simulator to perform functional simulation. So these are the steps that we're going to do today in the lab. Okay, so before we begin, let us understand about the various features with this Quartus Prime Lite Edition. As you can see here on the left-hand side corner, the project navigator, where in this space you can able to see the target device that I've chosen. So in this case, Intel Cyclone 4E EP4CE115F2937. So this is the device that I targeted. Okay, so it's a DE2115 board. This Cyclone 4 FPGA is available. Okay, and here you can find this is your project name. Okay, whatever the design that you are going to do, that's going to be your project name, and then you can able to see the hierarchy of this project. Do you have any lower level design? So in this case, I have some lower level design. So it will show what are the various hierarchy on your design. Okay. Now here you can able to see there are different drop downs are there: hierarchy, files, design unit, IP component, revision. So when you click on hierarchy, you can able to see the hierarchy of this particular design. Okay. Then you have file section where you will have all those files associated with this project. Okay. So .bdf stands for block design file, IP variation file, vector waveform file, and if you have any Verilog file, that also will come here. So you can see what are the files associated with this project design especially. Then you can see any design units that you have. That means when you're adding any library parameterized module or an IP or an user library from the library, if you choose, you will be getting those design units that have been used in this design. And IP component, if I use any IPs, then it will list what are the IPs that I use. So in this case, I used an adder and then a mux. Okay, so it shows those IP components. Then you can see revisions. So in this case, I have not made any revision. That means right now I'm executing a design project with the name Lab 1. After making all those compilation, if I want to, first time I've just done for area optimization. Next, I want to change the settings. I want to do it for timing. Then I can keep the earlier version as Lab 1 and the new version as a revision 1, so that I can able to compare between these two. Okay, so for that purpose, we'll use this revisions. Okay, later we'll learn how to do that. Now in hierarchy, you can able to see. So by default, it will be in hierarchy. Now coming to this particular window, this is a task window where the complete design flow steps you can able to see here. So when you compile your design, these are all the following steps will be executed. The first step is analysis and synthesis. So when you're doing a block diagram based design entry procedure, if you have any connections mismatches, okay, instance mismatches, then it will report it. If you're doing a Verilog STL based design entry, if you have any syntax error, then it will show what is the syntax error on your code. So that's the job of analysis. And synthesis, as we discussed earlier, whatever the Rtl code that you are writing or the schematic that you are going to do, it will map to the target technology. In this case, it is Cyclone 4E, and then it will get the equivalent hardware. Okay, so that's the job of synthesis. So you can able to see that in this step. In the next step, once it's completed analysis and synthesis successfully, it will move to the place and route. So we have seen in the design flow where the place and route will be done by Intel Quartus Prime automatically based on the IO information that you're going to provide. So whatever the functionality, so here you can see the add. So in which logic element I need to keep this adder, in which logic element I need to realize this adder, in which logic element I need to realize this mux 2 to 1. So all this placement of those functionality into the CLBs will happen in the placement, and how to interconnect them to realize that particular functionality, the routing will happen. So in Intel Quartus Prime, we call this step as a fitter. So what fitter basically will do, it do place and route. Along with that, it will do one more thing. So for example, your design, let us say, is requiring a more than 2 lakh logic elements to implement on a target device. Whereas in this case, I have 115K logic element only in Cyclone 4E. Then while compiling, the fitter will tell that I cannot fit this into the target device because the design requires more number of LEs, but whatever the device that you have chosen, it has not have sufficient LEs to implement. And the second observation, like, the number of IOs. So your design IOs and the FPGA pin IOs. So it should, within that FPGA IO range only your design IO should be. If it is exceeding the number of IO, again it will tell that it can't fit into the device what you have chosen. So that's the job of fitter, which plays and route. Then the next step, assembler, where it will generate the bitstream programming file. So it will generate a 2 set of programming file. One is SRAM object file, SO file. The other one is POF file. So this PROM object file. So these 2 object files will be generated by the assembler. Okay, this will be used for implementing into the target FPGA. Then you can able to see the timing analysis. So right now we are not going to concentrate on timing. Later, one separate session, we are going to discuss how to perform timing analysis. So basically, it will just tell you what is the operating frequency of your design. Is there any failed path? Whether all the paths are meeting the timing requirement. So your various timing related parameters that you can able to check. But user has to provide the constraints. That's very, very important. So we need to provide the constraints, and accordingly this timing will be checked. And finally, EDA netlist writer. So this will write a post-fitted netlist. Okay, so that you can able to see. So these are all the typical steps will run when I'm performing the full compilation. And you can restrict yourself to which stage of the design flow that you want to do it. Whether you want to do it for full design, or whether you want to do only up to RTL simulation, okay, or whether you want to do up to gate level simulation. So depending upon your flow requirement, you can choose it. So by default, I am doing that for a complete design. So that's a job that will happen, and then you can able to see the progress once it's completed. You can able to see the progress of each particular stage here. Then coming down here, it's a typical console window. This is a console window where you will be able to see the warning error messages here. So you can interpret easily. If it is green color, if the font is in green color, so it is successful. If it is in font in blue color, then there are some warnings. If the font is in red color, then there are some errors. Okay. So you need to go through the warnings and error, and then you need to fix it as much as possible. Okay. And this window also will help you in adding your ticket file directly. So in this course, we are going to learn graphical user interface only, GUI mode only. However, this also supports, running an automated script. Okay. So in this console window itself, we can able to do that also. Okay. And coming to this particular space, we call it as a workspace, where when you're opening a text editor, you'll be getting a text editor here, and then where you will be typing your Rtl code, and you will be able to open the schematic editor when you want to do a block level or schematic level design. So where the schematic editor will open here. Okay, and when you are compiling it, you can able to see the synthesis reports, summaries, everything over in this workspace. On the right hand side, you can able to see the IP catalog, intellectual property catalog. While you're installing the Intel Quartus Prime, you will be getting all these libraries. Okay, so starting from basic functions in terms of arithmetic functions, you can see you need not to write the Rtl code for this. Directly you can use, and then you can customize for that your application. Okay, so we'll see an example today in the class. And you have related to the clock, bridges, adapters, And then of course you have application. When you come to image processing application, error detection, error correction, filters. Okay, so these are all the IPs are available. So we'll use this throughout the, in our course for different design problems. We'll be using it. And of course, if it is not available here, then we will create that using, primitives, and then we'll make our own customized blocks, and then we'll integrate in the design. So that also we will do. Fine. Any questions so far? Okay. Now we'll see these different tabs here, starting from file. So throughout the design flow that we'll be using it. So in file and then new, you can able to see what are the various design files that Intel Quartus Prime supports. So it supports active HCL, block diagram schematic file, EDIF file. EDIF stands for Electronic Design Interchange Format file. So from one compiler netlist, you can directly import a EDIF format directly here. This is a QC system file when you want to do a embedded system application. Then state machine file, you can directly read the state machine directly. Then system Verilog, VHDL and all. But in this course, we'll be focusing on block diagram schematic and more on Verilog HDL. Okay, clear? Then so you will find a project wizard. So once you invoke the tool, the very first step you will be do the project creation. There are 4 to 5 steps involved in the project creation. So we'll use this new project wizard to create the project. Then you can able to see to open a project, to save the project, and to close the project. We'll use these tabs. Now there is an additional interesting feature that you can use here is create or update. So create HTML design file from the current file. So for example, I'm using a block diagram design file. I made a block. Now I want to generate a Verilog code for it. So I can use this create HCL design file from the current file. So it will generate automatically the Verilog file for the current defined block diagram file. And in the same way, you can generate a symbol file for the current file. For example, you are making your own customized block or schematic, then you want to make it as a block as such. Okay, so today in the lab class, we will take one example of it. So we'll make a customized design and then we'll create a symbol, and then you can use the symbol on your system again. In the same way, where you can, if you have written a HTML code and a part of it you have a block, then you can convert this HTML code into a block. So using create symbol file for the current file, you can convert that HTML into a block file. Okay, and then you can see what are the recent file, recent projects. Then coming to the edit, conventional edit option like cut, copy, paste, do, undo selection now, and then search option. And here view utility windows. Suppose when you are not able to see the project navigator, you can go to view utility windows and then click on project navigator, you will get it. Okay. So all those utility windows, by choosing it, you can able to see. Okay. Coming to the project, now you want to add or remove any files from the project. So you can use this option, add or remove files. So you'll be getting the what are the files listed in this particular design. So now I want to remove a certain file from this project, you can remove it. Or I want to add it, you can browse it and then go to the target location and then you can add it. So whatever you want to add. You can add it. Then revisions, as I already told. So you want to create a new revision, you can add this, and then archive project. So this also we will learn. So once you complete your design, you need to archive the project, and then you can share this among team members. This will, especially when you are going industry, you will learn about more on archiving a project, and then you will share among different team members. And you want to restore the archive project. Once you're getting an archive project from your team member, you can restore those archive projects. Okay. Coming to the assignment, where the device settings already I made, I want to change, after compilation, I want to change to a different device. Then you can go to assignment and then device, where you can able to see while installing, we have added Cyclone 4E family, Cyclone 10, Cyclone 4 and Cyclone 10. So you can able to see those device family. And then by choosing it, and then you can choose the necessary device detail, and then you can add it. Okay. And coming to the settings, this is a very important tab. Starting from, once you have created your project, you can able to see the top level design name, okay, and what are the files associated with that. Is there any specific library that you want to, for example, IP I have shown. When you're installing Intel Quartus Prime, there are certain IPs are available, but you are doing a design for that, there is no such IPs are available. You are procuring that from a vendor, you want to add that into it, right? So then you can use this option, and then you can browse the directory where those customized, the vendor library are available. Okay, so that components will be listed later on for you. Then IP settings, then operating settings, and here the EDA tool setting. Now by default, the Intel Quartus Prime inbuilt compilers will be used, but you want to use a specific sign-off tools from any other vendor, then you need to choose from the drop-down menu. So in this case, for simulation purpose, I'm going to use Model Sim Alpha. Okay. So if you don't require, then you can use none. Okay. Okay. And coming to design entry synthesis, and this is on the EDA tool. And coming to the compiler setting, this is very important. So as I told, when you are going for the synthesis, your input will be your RTL code. Then you need to provide a certain constraints. So here in this wizard, you can able to give the power and the area constraints. So by default, it will be in balance. So it will try to manage both the power and area. So I want to improve the timing. So I'm choosing performance high effort. You need to provide the constraints, clock related parameters also. Then it will focus more on timing. So that means you're not worrying about area. It may occupy more area to meet your timing. Now you are giving area. So that means you are compromising a little bit on the performance, but you want to ensure that the area occupied is pretty less. Then you can choose this option. And you want to do power, right? So you want to minimize area as well as the performance. Okay, moderate level is fine, but I want to optimize for power, then you can choose those options. So whenever I'm changing this, accordingly the algorithm used by the compiler will change, and then you can able to see the difference when I'm using balance, when I'm using performance, area, or power. The report will be significantly improved according to your constraints. Clear? And later we'll be seeing about how to use timing analyzer, where you need to provide a SDC constraint file. We call it a synopsis design constraint file. We need to add those so that the compiler will take those information and then apply to your design, and then it will check whether it is meeting your timing requirement or not. Okay. So already we discussed about assembler. It will generate a bitstream file, and signal tab to logic analyzer for doing a logic analysis. We'll use that, and a power play power analyzer. We'll use that for power analysis. Okay. So coming to the next assignment editor. So this will be used when we are going for the hardware implementation. So here directly, I can import the assignments, like using a CSV file. I can add a CSV file. It will list out what are all the IOs associated to that particular FPGA board. And then you can manually enter the IO details in the Excel sheet, and then you can able to directly map to the target FPGA. So for assigning that, we'll be using this assignment editor. And pin planner also we can use for assignment of IO, and then you can able to see the pin details of the chip. Okay, it's a bird's eye view. Okay, you can do it this way. And coming to the processing. So once you're done that, then you need to do a compiler design. So you can able to see this start compilation. Once you click this start compilation, it will perform all the tasks which I explained here in this task window. Okay, analysis, synthesis, filter, assembler, terminus, and even. Suppose you want to do individually. Okay, suppose you want to do it individually, then you can use the start option, and then whichever the step that you want to do, you can explicitly run that particular step, and then you can take that step. Okay, and here you can see this is a power analyzer tool. where you will do the power analysis. Okay. And coming to the tools, as I told, you can invoke a model sim simulator in this environment. So before going for the RTL simulation, you just ensure that under the options, then you can find the EDA tool option, and then you can see model sim altera. So this part, whether it has been assigned up properly or not, you need to check. Okay. So when you are clicking on RTL simulation, it will automatically invoke the model sim altera. So this part, by default, it will be available. Suppose if any directory changes has happened, then kindly browse it and then map to this location from the target installation directory. So this is very important to invoke model sim from the Intel Quartus Prime environment. Okay. So first you need to check this setting. Once this setting is done, then you can go to tools, run EDA simulation and then RTL simulation. It will automatically invoke the model sim and where you can do the function simulation. And then to invoke the time cost timing analyzer, we use this. And there are some advisors where the compiler itself will give you the certain advices to you how you can improve the performance, in terms of timing, power, and in terms of minimizing the resources. All these things it will give advice, and accordingly you can change the settings in the compiler. Thereby it will provide a better QR, the quality of the results. Okay. And chip planner, where you can able to see the bird's eye view of the target device. So in this case, Cyclone 4E device that we have chosen, right? So from the as a bird eye view, you can able to see. Now you can see just a blue colored, block. Now you can use this zoom option, and then you can left click on the mouse, and then if you zoom in, you can get this, right? So this particular array of these boxes we call it as a lab. Lab stands for logic array block. Lab stands for logic array block, and each one is a logic element. In the previous class we discussed what is this logic element and all, right? So each one of this box is a logic element. Okay, so you can zoom out, and then see in this particular target FPGA which you have chosen, right? You can see how many number of LEs are available. Almost 115 lakhs of logic elements are available. Okay. And there in this window itself, we can able to see where our device, our design has occupied in the target environment. So it will be highlighted in blue color. So later in a separate class, we will discuss about more on this. See here, our design occupies only in this particular lab, and that too only few logic elements you can able to see here, right? This highlighted blue color only has been chosen. Okay. Now coming to netlist viewer, after the synthesis, we can see what is the equivalent hardware logic that it has got generated. So using this RTL viewer, you can able to see that. Okay. So now you can see it shows in terms of block. If you double click on this, then you can able to see this is a basic adder structure. Okay, so the logic equivalent hardware logic, but you can able to see. And you can also see the technology map viewer before implementing onto the target FPGA. In actual FPGA, how it looks like. So you can able to see that also in terms of technology map view. Okay, so the data connections, everything you can able to see. Then coming to programmer. So here we'll use programmer to finally loading that SO file or PO file into the target FPGA. We'll use this programmer interface. Then IP catalog here by default will be available, or else you can invoke IP catalog from here. We'll use NIAS2 software and platform designer for system level design application, the last objective which I told in the lab introduction, right? So for that we'll be using it. Okay. And license setup we are not going to use for light edition. Only we are going to use that for standard and pro edition. In the lab we will use this license setup. And install devices, suppose right now you have Cyclone 4 and Cyclone 5, 10. If you want to add any other device using this tab, you can able to add it. After downloading, you can add it. Now we'll use these options which I told you already. For that, you'll choose a EDA tool option, and then you are ensuring that that is done. And one more thing that you can do is the processing, where you can choose how many number of cores that are available in your processor. If you have 2 cores, then choose 2. If you have 4 cores, then you can choose 4. So when compiling, it will use all the 4 cores, and then the way the performance will be little improved. So how to do it? Once you invoke the tool, go to Tools, Option, and then Processing, and then Maximum Processor. And Windows, you can detach window, close the windows, all these things, and help you can able to see the PDF tutorial for VxL and Verilog users. Okay, and about Quartus Prime, you can able to see which version and the details. Yes, so this is the overall, the view that I given. So over the period of time, we'll go in detail about each and every options, features available with Intel Quartus Prime. I'm just closing the project. We create a new project now. Any questions so far? Are you there?
Yes, sir. Sir.
Yes.
Sir?
Yes.
Sir, I have one doubt. Sir, why can't we simulate in Quartus only? Why we need model sim for
Actually,
waveform?
yes. Yeah, listen, here in Quartus Prime, just for university program purpose, they are given. It has a limitation. Okay. In a sense, like you cannot run a test benches here in Quartus Prime environment. Okay. Where you will be able, you need to provide the test bench. In this example, we are going to manually force IOs. Where you need to write the test bench will generate whatever the symbols that you want to run it. For that, we have to use model simulator only. Okay.
Okay, sir. Yes, sir. Thank you.
One more.
So, when I was installing the Quartus Prime,
Mm.
using your referencing one of your videos,
Mm.
so when I was installing, I didn't get the option of help Quartus help option.
Okay. In that,
Certain checks.
okay.
Huh.
Yeah, fine. In that itself, I given an executable called help and program. You try to install that executable also. Then you will get this option.
Executable help.
Help, yeah, Quartus help executable also is available in the repository what I given. You install that also.
Okay.
Then you will get this option.
So I have installed it already. So do I have to uninstall the whole Quartus Prime and install it again for
No
that?
need, no need. Just try to run that executable help, Quartus help executable alone.
Okay. Thank you, sir.
Any other doubts? So today we'll be taking a very simple example, schematic based entry, where we'll be so we are going to do this today. So it's a 1-bit adder. Okay. Now you have 3 inputs for this adder, and you will be getting 2 outputs, sum and carry. Now you have 2 to 1 mux. You have 1 bit selection line. So 0 and 1, it will select either sum or carry. Now it will come to the next stage where I'm going to connect that to a 4-bit SI-SO, serial in, serial out shift register. So this is a sequential logic where you require a clock for this. When you see this serial in, serial out, by this time I hope you might refresh the concepts. It requires a 4, I can model this using a 4D flip-flop, right? Then connected like this. Now what we need to do here is, first, very simple, we need to design this serial in, serial out. How we'll design? We'll use primitives. It's available in the library, D flip-flop, and then we'll make this logic. And now we'll make this as a customized block. Name it as SI-SO. Okay. That I'll be using in my design, okay, as a block. Okay, so I need to develop this, and then I need to make this as a block, and then I'll be customizing that I will be using in the design. This adder and this mux are available as an IP in LPM, library parameterized module. So I need not to design that manually using a logic gate, or I need to write a Verilog code to realize these 2 particular blocks. We will directly take from the IP library, and then we'll import that into our design easily. Okay, so this is a very simple design that we are going to do. Okay. So the very first step, we need to create the project. So once you invoke the tool, we will be landing up to this page. Go to File, New Project, Wizard. Okay. File, New Project, Wizard. Okay. Next, immediately, right? Generally, we will get a pop-up. We'll say yes or no. Please try to read what is given here. This is an introduction page where this new project wizard will help you to create a new project, and of course the preliminary project setting, which includes project name and directory, name of the top level design entity, the project file and the library, target device family and device, and EDA tool settings. So these are all the steps I'll be going to do in the creation of the new project wizard. Okay, so we'll see one by one what it is. The first step in the project creation is you need to set the directory, the name of the project, and the top level design name. So by default, it will show C drive and then your installation part. Create a directory, and maybe you can create one more directory within that also. Okay. So I created it. And now, what is the name of this project? Okay, so you can keep whatever you want, but try to keep related to your design. Okay, and when you're typing the name of the project, you can see it is coming automatically here. So the name of the project must be similar to the top level design entity name. Okay, that means when you're writing a Verilog code, there is something called module name. So your design project name and module name must be same. It should exactly match with the word. So it is case sensitive also. Okay. So by when you're typing here, it will automatically come here. Okay. Clear? So in this page, we have given the directory, target directory we created, and the name of the project we have given. Okay. Just click next. So it will ask that it does not exist. You want to create the directory? Yes. You want to create it. Now in the project type, there are two types. One is the empty project where you will be creating a new project by providing a project file, library, target device, so and so. And the other one called the project template, where using this design store, it will direct you through the Intel FPGA website. And then with your user credential, you can download from the source certain project settings or the project template. So in this example, we are not going to use this project template. We'll be using the empty project. So that means we are going to create a new project by providing the necessary information. Click next. This is the add file section. Suppose already I have my source file. I need to add that to the project. So I have written a Verilog code. I want to add that Verilog into my current project. Then you can add this using this browse, and then you can go to the target directory, and then you can open, and then you can add it. Okay. Similarly, the block files also. If you want to add any block file, you can add in this way. But right now, I'm not going to add any of the file. I'm going to create a new file after creating the project. Okay. No existing file I'm going to add. Here you can see specify the path names of any non-default library. So what does it mean? You have Intel Quartus Prime installed, and then you can see there are certain library options which you've seen here, right? Apart from that, as I told, when you're getting certain libraries from the vendor, so you'll be putting in your target drive, and then you can browse it, and then you can provide the path. Okay. So when you are invoking a block diagram schematic with schematic editor, you can able to access those blocks. Okay. So for that, you can add the path of this particular non-default library if you have anything. Otherwise, you need not to use this tab. By default, whatever the library that I have, I'm going to use it. Just click next. So this is a very important setting where I'll be choosing the target device family, device number, and board related settings. So it lists Cyclone 10LP, Cyclone 4E. So you should be very clear on what is the target device that you're going to implement. So whatever I have in my hand, that device details, part details that you should have. Okay. So Cyclone 4E is a target device that I have. And if you put Cyclone 4E, and then there are n number of devices are listing here. Okay. It's again a very difficult task to shortlist. So here you can use from the available device list, you can shortlist by means of the package that I am using for Cyclone 4E. So the package type that FPGA which is coming is FBGA. FBGA stands for Fine Ball Grid Array Packaging Type. Okay, these steps are Fine Ball Grid Array Packaging Type. And then if you know about number of IOs, then you can able to shortlist it. So it is 780, and speed grade, it is about the logic element latency. So I've chosen 7. Here there are two features are there. The target device, auto device selected by the fitter. Just now we discussed what is fitter. So fitter will go and choose the target technology, CLBs, placing those functionality into the CLBs and routing them together, right? When I'm choosing auto device selected by the fitter, that means that I'm not going to target on any hardware, exact hardware in my FPGA. I just want to see my design can able to fit in any of the devices which is part of, Cyclone 4E family. Okay, so whatever listed here. So that means you cannot implement that over a target hardware. So if you are having a specific product with you, the FPGA product with you, which you want to target it, then you must choose a specific device selected in the available device list. So always choose this specific device selected in available devices list, Cyclone 4E, and then this is for just shortlisting the device detail. And now you just drag down, you will be getting the device detail EP4CE115F29E7. So this is the target device that I have in my hand, and then I'm choosing that particular device here. So it has a core voltage, logic element, total IO, GPIOs details you can able to see here. These are the basic information about this particular device. Okay. So here what I'm doing in this page, I'm just choosing the device family, and then I'm just shortlisting the device with the help of package, pin counter, and the core speed. And I'm choosing specific device from the selected device list. And then I'm choosing EP4CE115F2937. This is the device. Just click next. Now here you want to have any additional EDA tool setting. For example, for synthesis, if you have installed the precision synthesis or Simplify Pro, you want to use that for the synthesis, then you can use it, provided it should have been installed. And I already told in the options, you need to give the part where it has been installed, right? So right now, I'm not going to use any other EDA tools for design, entry, and synthesis. Are you going to use anything for the simulation? You can use models in Altera, and then you need to provide a path for the simulation. For this example, I'm not going to use models in Altera also. And similarly for the board level, so and so. So by default, you keep other settings as it, and then click next. Now, whatever we have done, it is being listed here as a summary. The project directory, the project name, top level design name, and then family that you've chosen, device detail, and then design entry. We have not added any EDA tools here, right? And for this target device, the core voltage and the junction temperature. Click finish. Okay. Now you can see under the project navigator, the device, whatever you have chosen, and the project name. Okay. So if you double click on this, it will tell that can't find design entity, my design. So what does it mean? I have not added any design to this project, right? Now my next step is to design it. So just now we have seen, this is what we are going to do now, right? So to do that design, we have to go to File, New. Here you should choose block diagram, schematic file. Okay, File, New, block diagram, schematic file. Just do OK. Now you will be getting the schematic editor. So in this schematic editor, you will be having various tabs. You can understand once you start using it. Okay, and this is the important where the symbol tools. So where it will direct you to the library. It is available in C 18.0 Quartus library. And then if you expand it, you can able to see the various directory. And under the primitives, you will be having no logic. All these basic logics are available in this. Okay, and then we'll use this for the interconnection of single bit data, and then for bus data, we'll be using this bus too. Okay. So as I told earlier, for this particular design, first we need to make this particular serial in, serial out, and then we need to convert that into a block symbol file, and then we need to integrate that in our actual design. Am I right? So in order to do so, first we will be creating this shift register. For that, I need a D flip-flop, 4 numbers of D flip-flop. So how to do it? Just click on this symbol tool. You will be getting the library expanded. Under the primitives, you can see storage, and then you can see D flip-flop. Just give OK. After choosing it, just give OK. Now when you are bringing to the schematic editor, you can see the image of it, right? So by left click on the mouse, you can place it wherever you want onto the schematic editor. Again, it will be available. So wherever you want, again you can place it. Again you can place it. So to disable this option, you can use escape ESC key in your keyboard, okay, to deselect it. Okay. So now I've chosen a D flip-flop, right? So this D flip-flop, you can zoom it and then see it has a clock input, and then it has a D input, and it has a clear and preset and Q output. So for simplicity, we are going to use D input clock only. We are left open this preset and clear signal, okay, for this example. Okay. If you want, you can connect that with the clear and preset signal also, but for this example, we are not going to use it. Now we need to make the interconnection, right? So first of all, we need to add the ports. What are the ports required? So for this overall design, one port is required for the first flop input, for the data input, and then another input port for the flop, which I'll be connecting across all 4 flip-flops, and then one for the output port. So how to choose a port? Here you can see the pin tool, drop down will be there, and then choose input. Now you will be getting the image of the input port. Thank you. So you'll be getting the image of that port, and then you can place wherever you want. Okay. And then we can adjust it. So I require one for D, the other one for the clock, right? Now the next one is output port. Again, from the drop down, choose the output port, and then you can place where you want the output port. Okay. So now I'm going to make the interconnection through the orthogonal node tools. Okay. Before that, you just zoom it. Always advisable to zoom it. Okay. Use Control Z to undo also. Now, how to connect it? Choose this particular orthogonal node tool. So from the port you want to connect it, right? So just place the cursor, hold the left click of the mouse, and then drag it wherever you want it to take. Just hold and drag. Okay. So use this grid effectively. Again, I'm repeating. Just choose the orthogonal node tool, keep the cursor, hold the left click mouse, and then drag it, and then leave the left click mouse wherever you are. Okay. Again, I'm choosing that same tool. And then I'm connecting it. Again, now I'm connecting to the input. So when it is connecting to input, it will show you a square box where you can connect perfectly. The same way, left click, hold, drag, and then leave. Again, left click, hold and drag. Then left click, hold. Okay, so we have made the clock. So you can unzoom it and then see we made the clock. Okay. Now we need to connect this input port and change this selection. Right, and now again choose a orthogonal node tool. Suppose if the input is 2-bit and here also you have a 2-bit, then you should choose a orthogonal bus tool. Okay, for a single bit data you have to use orthogonal node tool. Now what I need to do, the output of the first flip-flop is connected to the second. Similarly, the output of second is connected to the third, and it is connected to fourth. And finally, the output. So we made the connections. First up, place the components, place the input and output port. Then you need to interconnect it. One more step is we need to name the IOs. So you can right click, properties, and now you can give the pin name. I'm giving it as D here. And you can double click and then you can rename here also. Either way is fine. So this is the clock CLK. And then DR. So you can see D clock and DR. So now I made the connections and then I have named the ports. Next step, I need to save this. Now save this. By default, it will show that as a my design, but this is not going to be my top level design because this serial in serial out, we are going to use it in the top level my design. So now this is a lower level block. I'm naming it as SISO.BDF, block diagram or schematic.
Sir, excuse me, sir. I have one doubt.
Hmm.
Sir, what will be the clock frequency we need to insert?
Those things we are not going to do now. See, all right now we are doing only the functional design aspect. Okay, the actual clock frequency, those things will come in the hardware only. Actual clock will talk only in the hardware. Right now, in this lab objective, we are going to design it, and while performing the simulation, we are going to assign the clock frequency. Okay. Right now
Yes.
we are just we are not going to connect a crystal oscillator or PLL to connect to this clock. Okay, so that we are not going to do. Just a port. Then we are going to apply for the design purpose. We are going to apply a clock signal. That's it.
Okay. And if one netlist I have drawn, then if I want to delete it, then which button should I press?
You want to delete something?
Yes, sir. Suppose I want to delete the
Yeah,
output
you
row.
just so that's what you just select whatever the component that you have. You just keep the
Okay.
cursor, select it, and then use
Okay.
delete key in the keyboard. Delete option is there, no? You can use that.
Yes.
It will
Okay.
delete, or
Okay, sir.
right click, or you can right click. You can delete it. Okay.
Yes, sir. Thank you, sir.
So right now I've saved this as a CISO. Okay, I'm not saved as a my design because this is not going to be my top level design. Then after making that, after saving it, I need to check whether I made these connections things properly. Okay, so go to processing, and analyze current file. Go to processing and then analyze current file. You can able to see it's processing on the right hand side bottom. It will show the percentage. So it's completed. You can see 0 errors and 1 warning. Warning is highlighted in blue color, as I told. Okay. So this is related to setting up a processors and all. So you can ignore this warning now. So the connection is fine. Now you can do full compilation. Go to processor, and then you can do a full compilation. So you can able to see when I'm doing full compilation, it's showing the percentage of these stuff. Right? So anyway. Okay. So this specifically I just want to explain. Now what it is showing an error, the top level design entity is my design, which is undefined. What does that mean? Here I named that SISO, but this is my design. Alright. So this is a lower level block. So you can ignore this error. Right now we need to convert this particular block into particular shift register into a SISO block. Okay. So we'll proceed to that. Go to file and then create or update. You can see the option create symbol file for the current file. So the current file is siso.bdf. So now we need to create a symbol file for the current file. So just click on that. It will ask the directory. I'm using the same path under the lab file. Now it will be saved as .bsf. So it will convert into the functionality will be converted into a symbol file. So just save it. Now created a block symbol file in siso.bsf. Okay. So the job is done here. Now our objective is to now go for this particular design. Okay. So what I require an adder, I require a 2 to 1 mux. Now whatever the CISO that I've done, that also I require now. So to do that, go to file, new, again block diagram schematic file, and then view OK. Fine. So you got the editor back. Now here on the right hand side, you can see the IP catalog. If you're not getting here, it will be available under the tools IP catalog. Okay. Now you have a search tab here. I want an adder. So I'm going to type add. Then you can see the variety of adders are there. So here, as I told, I'm going to use library parameterized module. So I can customize it according to my requirement. So choose at LPM add underscore sub. So double click on this, you will get a pop-up window. Now this will be saved in a name IP variation file. So I need to choose whether I want a VHDL type or Verilog type. So I'm going to choose Verilog, and then I'm going to give the name for it, adder. Okay, let's give OK. It is also going to save locally onto your project directory. Okay, so the name is important and the type is Verilog. Just do OK. So now you will get a MegaWizard plugin manager. You can customize this particular adder depending upon your requirement. Now in this case, you can see here how wide should the data A and data B inputs must be, right? So you can choose starting from 1 bit down to 256 bits are there. Now in this example, I'm going to choose 1 bit. Whether you want to perform an addition operation or you want to design a subtraction operation or you want to create an add cell. So in this case, I'm going to do only the addition. So by default addition, and then I will change that to 1 bit. Just click next. Now it is asking whether these values are constant. You want to provide a constant value to the input ports, then you can choose this option, whether it is logic 1 or logic 0 permanently that you can give, whether you want to have a signed addition or unsigned addition. So now I'm going to do unsigned, right? So by default, you click as such. And now you want to have any additional input, that is carry input for this adder. Yes, I want a carry input. Do you want a carry output for this? Yes, I want to carry output. So you want to do a pipeline concept? No. So right now I'm not going to do that. Just give next. Give next. Now it will ask you what are the files to be generated. So you can turn on the files you want to generate. So one is the block level.v file, instantiation.v file, and this is very important because we are going with a block or schematic based design file. So you need to have a Quartus Prime symbol file for this adder. So this entire adder will come as it as a symbol. Okay, so just choose it and then click finish. Okay, now this symbol file has been created into the target directory with the name adder.qip with the same project directory. Okay, clear? Now I've created this 1 bit adder. Now I'm going to do the 2 to 1 mux. So again, the same way, type mux, then you will be getting LPM mux, double click, then you can use mux 2 to 1. Sometimes the keyword, if you're using the same way, it will give an error. So try to use a different name. Okay, mux it the keyword. Same Verilog, same directory, just do OK. And how many data inputs you have? 2 bit. How many data? 1 bit, 2 to 1 max. Okay. Then give next. Then give next. Then choose the block symbol file and .v file, and then finish. Okay. So whatever the 2 IP variation file that I've created is now available in my project directory. And also the serial in, serial out, just now I converted that as a block symbol file, that also available in my project directory. Now I am ready to make this particular design, right? So how to do that? Go to the symbol tool again now, and now you can able to see one more directory, project. So this is my current project directory. So under that, you can see the adder that I've chosen from the IP variation file, mux, which I've done with the IP variation, right? So from the IP catalog, and you can also see the serial in, serial out that I've created, customized from my side, right? So just choose this adder and then click OK and keep the block. So I need only one adder for this. So use escape, deselect it. Again, go to the symbol tool, choose mux 2 to 1, and then again escape, and then again. Now serial in, serial out. Okay. So whatever serial in, serial out that we decided is a 4D flip-flop. Now I converted into a equivalent symbol out of it, and it has a necessary ports, whatever the ports that I have chosen, right? Now, what's the next step? We need to identify what are the ports required for it. So here the input ports. So there are 3 ports are required. One is for the carry input, B, A, and this one for the selection, and this one for the clock. And we choose output. Now we can zoom it. So you can adjust by using this arrow option, grid adjustment that you can make it to align so that the connections can be made much easier. So again, it is a 1 bit only. So I'm going to use orthogonal bus node tool. Left click, hold, drag, and then leave it. Okay. And so I've connected output port, mux to serial in, serial out, clock port, selection line, and from the adder output to the mux input. So the left out is the input ports from the adder. This orthogonal node will not do this. It's 1 bit. Can able to see that thickness of the line, whether it is a node tool or the mesh tool. And so I made all the connection. Next, I need to rename the pins. I've connected 14. So I completed it. Then zoom out and then see. Right. So this is what I need to do. Right. So I've done that. Next step, we need to save this. Now this is my top level design. So it's going to be my design.bds. Again, you need to check, go to processing, analyze the current file. Do you have any questions so far?
Sir, why is the input given as VCC, sir, always?
No, it's an input here, not always the input. Whatever the value that we're going to get, it's a port actually. It has a property of VCC, that's all. Nothing to do with your supply voltage. Whatever the value that we're going to force. Yeah. Successful again. Now, before we proceed, we need to do a very important step here. Under the project navigator, you can see the files. Now it shows siso.bdf, mydesign.bdf, right? So now choose mydesign.bdf, right click, now set this as a top level entity. So the tool will now understand that this is my top level design. Okay, and then you can cross check it by double click on my design. It will open this particular .bdf file. Okay, not the SISO. Okay, once you have done this, then you can go for the processing and start configuration. So you can see the progress here. Analysis is completed. And here you can see the here pop-up total logic elements. Only 4 logic elements it has used.
For that setup, we have to go to and
So once it's completed, you can able to see that message. So 0 errors and 14 warnings, and then through the warnings. So this SDC file for timing analysis. Timing recordings are not been because we are not providing any constraints. So that's one you can ignore. Now we have done the compilation. The next step, we need to do the simulation. Okay. To perform the simulation, go to File, New, and here in the verification debugging file, USD program VWF. VWF stands for Vector Waveform File. Okay. Give OK. Now you will be getting a waveform editor. Okay. Now in this waveform editor, I need to load all the IOs of my design. Right. So coming to the IOs of my design, going to be A, B, C, selection line, clock, and then out, right? So here in this workspace, just double click left, double click here. You'll be getting a node finder. Just click on node finder, pins all, and then list. You'll be getting all the pins of your design. Just select all, and then here you can find the symbol, copy to the selector node list. Just click on that. It will be copied to the selected nodes, and then just give OK, and then now just give OK. Now you can see here all the sports are listed. So you can click and then drag wherever you want to order yourself. Okay. Now you can do it. Now here in this waveform we can make certain settings. By default it shows nanosecond. You want to change the time unit, so you can able to change it. Now I'm just going to keep the simulation runtime window. Go to edit and then set end time. Okay. So I'm keeping the total runtime for 500 nanoseconds. Now you can see here that the exact window, simulation window is going to be 500 nanoseconds. Then go to edit, then grid size. So this grid size is nothing but this the rotating. You can keep 10 nanoseconds or depending upon your requirement, you can change it. So once you're done that, you need to provide the inputs to A, B, C selection and then clock, and then simulate and check the output. So I can use left mouse drag and selection certain time period time, and then you can use high, low, whatever the value that you want to assign. Okay. So right now I'll just explain in a simpler way. Just I'm going to choose this center value. Okay. And then I'm going to use this count value, and I'm keeping that as by default, let us say 4 nanoseconds. So what does that mean? It is not a clock. Don't misunderstand there is a clock. So at every 4 nanoseconds, I'm toggling the value of A. Now coming to B, again you can count, and then you can toggle this value to 6. Again C, and toggle this value. Okay. so that you can able to see here the values are like 0, 0, 0, 0, 1, 0, so all those possible numbers. Or else manually you need to do it. Okay. Right now, for understanding purpose, I'm just keeping this A high, B high throughout the simulation window, and C is low. Now selection line, and then I'm using the command every 100 nanoseconds, going high, low, so that I'm checking for logic 0 as well as logic 1. Now you need to provide clock. So one of your friends asked question how we will be providing clock. So go to edit, value, and then override clock. Now here you will get the clock period. So this is basically T, and then you can convert F is nothing but 1 by T. And then you can also adjust the duty cycle according to your requirement. So I'm keeping it as 10 nanosecond with a duty cycle of 50%, and then give OK. So now you can able to see here. You can use the zoom option, and you can see. Right? So this is a 5, and this is a 15. It's 10, right? So we are given the inputs. Now we need to simulate, and then we need to see the output. Before that, we need to save this file. Go to File, Save. So you can give default name or another name. Dot VW vector waveform file. Save it. Go to simulation, and then click on Run Functional Simulation. Now you can get see the another waveform editor, you got the output. So when A, B are 1 and carry is 0, what is sum and what is carry? Sum will be 1, carry will be 0, right? The sum is 1 and carry is 0. Now this is a selection bit of the multiplexer. When selection is 0, it is choosing the sum, okay, output. When selection is 0, it is choosing the sum output. When selection is 1, it will be choosing the carry, right? So now I'll be seeing this output, right? I'll be expecting here, but there is a delay. Why? Because it's a 4-bit shift register only we have designed, the last block, right? So you know the output you will be getting after the 4th clock cycle. So by this time, I hope you know how this shift register works. So if I'm giving 1, after the first clock cycle, it will come here, this 1. After the second, after the third, and after the 4th, I'll be getting that 1 over here, right? Now you can able to see from the, you can use this cursor, and then you can see that my selection A, B are 1 and C is 0. We know sum is 1 and carry is 0, and selection is 0. I should get the output as 1, but I'll be getting after 1, 2, 3, and then 4. So after the 4th clock cycle, I'll be getting my output. Again, I change the selection to 1 here, but after 1, 2, 3, 4th clock cycle only, it will become 0. So the carry output. Are you clear? So I have functionally verified my design. Okay. So that's how we need to do the functional simulation. So today what we will learn is what are the various features of Intel Quartus Prime. Second, we understood about how to create a project. Then we have created a design using block or schematic based design entry. And then we make our own customized block, serial in, serial out, shift register using the primitive. And then we instantiated that into our actual design. And then we have used two library parameterized module, one for the adder, the other one for the multiplexer. And then we made our design. And then now we have functionally verified our design. Okay. So that's all for the day. If you have any questions, I will address.
Sir,
Yes.
sir,